First of all, I thank the organizers for giving me this nice opportunity. And this is my second QIP conference and the second QIP talk. The previous one was QIP2020, just before the COVID-19. So I'm very happy to be a part of this conference, on-site conference again. This talk is based on these two papers. The first paper is collaborated with Keiji Saito at Keio University, and the second paper is collaborated with Ryuji Takagi at NTU and Yui Kuramochi at Kyushu University. Let's start. I start with the topic of today's talk. The topic is a universal trade-off relation between symmetry, irreversibility, and quantum coherence. These three concepts are foundations in physics. Symmetry is the guiding principle in modern physics. It plays central roles in high-energy physics, condensed matter, and quantum information theory. And irreversibility is a central concept in thermodynamics and stochastic mechanics. It is also related to quantum error corrections. And quantum coherence, quantum superposition, is a unique property of quantum mechanics. It is the origin of quantum advantage in many tasks. My main result is a universal trade-off relation between these three. This is the main result. This inequality is very simple, but has many applications. For example, quantum computation, error corrections, measurement theory, quantum thermodynamics, and black hole physics. Hereafter, I will talk about the setup of the main result and the main result itself, and after that, I will introduce the applications. Let us discuss our setup. We consider two systems, A and B. These two systems interact with each other as a unitary dynamics, satisfying a conservation law of X. We can consider more general Lie group symmetry, but in this talk, we focus on this type of symmetry for simplicity. And we fix the initial state of B as an arbitrary state, rho B. Then, the local dynamics from A to A prime is described as a CPTP map, E. For this setup, our result always holds. This is the result. In this inequality, there are four quantities. The first quantity is a change of local conserved charge, XA, by the local dynamics, E. The second one is the quantum coherence of XB in B here. Quantum fluctuation of XB, the local charge. And the third quantity is the irreversibility, delta, of the local dynamics E. And the fourth quantity is a just positive constant. So we see the definitions and important properties of these quantities. The first quantity is irreversibility. This is a function of the local dynamics E, this, and a test ensemble, Pk, rho k. We can choose this test ensemble freely, so we can take the arbitrary sets. And the formal definition of the irreversibility is this. Here we prepare some test states, test ensemble, and prepare as local dynamics, this. And after that, the initial states become different. So we try to recover the initial states as close as possible by using a CPTP map, R. But in general, we cannot recover the initial states perfectly. So we can define the recovery error for each initial state. Here, df is the purified distance, which is defined by this. This f is the Ullmann's fidelity. And we define delta as the minimum average of the recovery error for each initial state. The important property of this irreversibility is that the delta gives lower bounds for various irreversibility measures. For example, it bounds the entropy production, which is the standard measure of thermodynamic irreversibility. And it also bounds the entanglement fidelity recovery error. It is well used in quantum error correction. And it also bounds the Petz map recovery error. So we can substitute these irreversibility for here and use this inequality. So this inequality has many applications. And the second quantity is the quantum coherence of the XB, quantum fluctuation XB in row B measured by the quantum Fisher information. We use the SLD quantum Fisher information for the state family, this state family. And the definition is this. And the important property of the SLD quantum Fisher information is that it is a standard measure of the resource in the resource theory of asymmetry. So this is the trade-off relation, irreversibility and resource. And the second property is that it is a standard measure of the quantum fluctuation of X. Here, F low X is equal to the minimum average of the variance of this quantity X of the pure states psi j. Here we take minimum and the ensemble qj psi j runs the pure ensembles of row and including non-diagonal pure ensembles. And the third quantity is the degree of change of local charge. This is the formal definition. This definition is a little bit complicated, but the meaning is simple. To see the meaning, let's see the focus on this operator YA, here and here. YA is the operator of change of local charge. Here, E dagger is the dual of the local dynamics E. And the important property is that when the test states rho k are orthogonal pure states psi k, then she becomes like this. So she is the sum of absolute value of non-diagonal parts of YA, this operator of change of local charge. And the second property is when E changes XA non-trivially, I mean when the change of the XA is not just shift of the origin, then she is strictly larger than 0. So we can interpret she as the degree of change of local charge. Now let's see our main result again. There are two terms in the right hand side, and this square root delta is valid for always valid for arbitrary test ensemble, and delta is valid for test ensembles whose test states are orthogonal each other. I mean, fidelity between rho k and rho k prime is equal whenever k is not equal to k prime. And the message of the main result are these two. The first message is when she is strictly larger than 0, then delta is also strictly larger than 0. So when E, the local dynamics E, changes the local charge non-trivially, E, the local dynamics, must be irreversible. This is the first message. And the second message is the coherence in B here can mitigate the irreversibility. In fact, when the F becomes large, then the left-hand side becomes small, so we can make the irreversibility small. We can check this effect with using many concrete examples. So the take-home message is this. Under global symmetry, local charge cannot be changed without irreversibility. But the irreversibility can be mitigated by quantum coherence. So we call it symmetry and irreversibility and quantum coherence trade-off. Now we have obtained the main result. We found a universal trade-off relation between symmetry, irreversibility, and quantum coherence. But what is the trade-off good for? Fortunately, this trade-off relation is useful for various situations. Let's see the applications. This is the list of the applications, but this is a little bit complicated, so I simplify it. This is the simplified list of the application. It's here, the first application is quantum information processing. There are various restrictions on quantum information processing imposed by symmetry. For example, for measurement, there is Wigner-Araki-Yanase theorem. This theorem, this Wei theorem, says that when we try to implement measurements under conservation law, there is a trade-off relation between measurement error and coherence cost. And for unitary gates, similar theorem also holds, unitary wave theorem. Unitary wave theorem says for the implementation of unitary gates under conservation laws, implementation error is inversely proportional to the coherence cost. I mean, here coherence cost is the fluctuation of the conserved charge, so Fisher information. And for error correction, there is Easton-Near theorem. For covariant codes, recovery error is inversely proportional to the number of qubits required by the code. And there are many results related to the theorem. And the SIQ trade-off behaves a unified theorem of these restrictions. It recovers and extends these results as corollary. Here, let's see the mechanism of the application. So why this can recover these theorems. These theorems treat the trade-off relation between error and resource. For measurement, the resource, for measurement and for unitary gates, resource is quantum coherence, quantum fluctuation. And for covariant codes, resource is the size of the code. And this SIQ trade-off relation is a trade-off between irreversibility and resource. So by focusing that error of the information processing is a kind of irreversibility, we can derive these theorems from here just by substituting some specific setup in our settings. So the take-home message is SIQ trade-off, a unified theorem of restrictions on quantum information processing by symmetries. These restrictions are so special cases, special aspects of this type of theorem. And now I talk about the first application. Next, I talk about the second application. Second application is thermodynamic processes. Here, for simplicity, we consider the single bus case. Of course, we can consider the multiple bus case, and but in this talk, we focus on this type of single bus case. In this case, we can formulate a thermal process like this. We consider the system S as the cylinder of heat engine, and we also consider the heat reservoir and other system C. This C can be coherence battery or catalyst or work stage or composite systems of these things. And we perform a unitary dynamics satisfying energy conservation law. Then we can apply our theorem to this situation by considering S as A and RC as B. And because Gibbs state do not have coherence of energy, we can evaluate the amount of coherence in C by our theorem. Then we can derive this theorem for the implementation of arbitrary channel E. Here, sigma is the generalized entropy production, defined as this, and F cost is the minimum necessary amount of coherence in C to implement the arbitrary channel E. And when E is Gibbs preserving, sigma becomes the normal entropy production, which is the standard measure of thermodynamic irreversibility. So this inequality shows a trade-off relation between thermodynamic irreversibility and quantum coherence. Here we remark that this inequality also valid for arbitrary channel, even if it is not Gibbs preserving. Now I talk about the third application. Third application is black hole physics. Our target of the application is Hayden-Preskill Salter experiment. In this Salter experiment, Alice trashes her computer diary in the original paper into a black hole, and Bob tries to recover the data of the Alice's diary by using Hawking radiation from the black hole. Here, the important point is that Bob have collected all radiation since black hole emerged. So he can use not only the the radiation emitted from the black hole after Alice trashes her diary, but also the radiation emitted before Alice trashes her diary. Then the question is, how much radiation does Bob need to collect to recover the original information in Alice's diary? Our result is applicable to the situation. But before seeing our result, let's see the Hayden and Preskill's original analysis. They assume two assumptions. The black hole, computer, and radiation consist of qubits. And the dynamics of the black hole is a typical Haar random unitary. Then they derive an upper bound of the recovery error of the information like this. Here, L is the number of the qubits collected, which is collected after Alice trashes her diary. And K is the size of the information in Alice's diary. So this inequality says when L is a little bit larger than K, Bob can recover the information in Alice's diary almost perfectly. So they say black holes are informative mirrors. This result is rigorous and very interesting, but they do not assume energy conservation. So the natural question is that what happens when energy conservation is assumed? Several pioneering works suggested that information recovery gets late in such cases. And in particular, a lower bound of recovery error is given in this paper. But previous lower bound needs extra assumptions and approximations. Our theorem gives rigorous lower bound of recovery error without any extra assumptions and approximations. So here, this is the result, and we use these two assumptions. We use the assumptions the same as what is this? This is black hole. Sorry. This is black hole. But assumption is the same as Hayden and Preskill used. And we just add the energy conservation. We can derive this result. From more weaker assumption, but in this talk we focus on this type of assumptions. And this inequality here, gamma is the remaining ratio of the black hole. So this inequality states that information recovery has inevitable error depending only on the remaining ratio of the mass of the black hole. Here, let's see the difference between the original analysis and our result. Here, this is the result without symmetry, so without conservation law. Then the recovery error decreases very rapidly. And our result, which is the lower bound, when there is energy conservation law, this bound holds, so the recovery error decreases, but the speed is very slow. So our result rigorously shows that energy conservation changes the speed of the information escape from the black hole radically. Our result also restricts the classical information recovery. So this is the result, and this is the average Hamming distance of recovery error, and gamma is again the remaining ratio of the black hole. When we throw this inequality says that when we throw classical m bits, about m over 4 bit will be unrecoverable until the black hole almost evaporates. Now I summarize my talk. We find a universal trade-off relation between symmetry, irreversibility, and quantum coherence. It has various applications: thermodynamic processes, measurements, error correcting codes, computation gates, and black hole physics. And I think we can more generalize and find more application of this result. So if you are interested in that, let's discuss together. Thank you very much.
Thank you. Very interesting talk. And we have a first question. Thank you for the talk. I was interested in asking about this bound. So, first of all, this constant here, like the delta.
This large delta. Okay. This can bounce other quantity. For example, the height of the conserved charge. So the difference between the minimum eigenvalue and the maximum eigenvalue of
so
the.
it's depending on what system you're studying.
Yeah. So this is the conserved charge in A. So yeah. Of course, we can bound this value with using other quantities, but now I say so. Height is it's the most simple one.
Okay. And so the bound overall, is it like generally tight, or it's?
Yeah. That is a good question. And this I think this is very tight because it recovers these three theorems. And these three theorems are optimal, are known optimal. So that fact that we can derive these from this is a kind of it is optimal in special cases. So I think this is very tight.
Thank you.
At least At least for this bound. This bound is maybe weak. Yeah.
Thank you for the nice talk. So can you obtain the opposite side of these relations?
So you mean upper bound? Yeah. That is very interesting. But for special cases there are upper bounds. But in general case, I don't have any upper bound. Maybe that is a very good question.
So thanks for the talk. I think it's a very interesting result
thank you.
got here. Can we switch to page 12 for once?
This one? Which one?
Page 12.
Page
1, 2, 12. Yes.
Here?
That's too fast. Yes, that's it. Thank you.
This
this F that you define here is this a measure of asymmetry?
Asymmetry. So yes. So the resource in the resource theory of asymmetry.
But you interchangeably talk about resource theory of coherence.
Resource theory of asymmetry, we treat the unspeakable coherence, and resource theory of coherence, we talk about, we treat the speakable coherence. So the type of coherence is very different. So I don't have the result for the speakable coherence. Yeah.
Okay, so this is strictly asymmetry, right?
Yes, strictly for the asymmetry.
Okay.
Yeah, asymmetry type coherence.
Okay,
yeah.
Okay. Thank you. That's it.
In deriving the upper bound for the error rate in the black hole evaporation, what metric do you assume?
Evaporation.
Yes.
So evaporation means black hole.
Yes. So what metric do you assume?
Sorry, please say again.
What metric do you assume?
What metric?
Metric of the space.
Metric. Yeah. So metric. What? So you mean the metric for Fisher information? No.
No, the metric of the space-time for the black.
Okay. That is important point, but maybe I cannot answer because we just use the Hayden-Preskill model, so random unitary model. It is just a qubit and her random unitary, so it is not considering about the time-space metric.
In Hayden's result, they used it for like a Schwarzschild style metric, but if we change the geometry, then the
yeah, maybe, but I don't know. Sorry.
Thank you for a nice talk.
Thank you.
So I confess I don't really quite understand the definition of irreversibility on the fly, but this looks very similar to me, like the quantum Cramer-Rao bound in quantum metrology. Is there a connect
Yeah.
between delta and like the uncertainty in measuring a parameter? Or?
Yes. Maybe we can applicable maybe we can apply this result to such such topics, but I didn't do it. So yeah, so maybe that is very good application.
So thank you. We need to stop here, so we can ask question to Hiroyasu after the session. Thank you.
Thank you very much.